Drugs, pesticides and fertilizers are crucial for our survival. However, they may contain impurities with harmful side effects for people, animals and our environment. One of chemical manufacturing's biggest challenges is to produce materials that can specifically perform a pre-designed function and to eliminate contamination of undesired substances. The CISS effect serves this purpose, applying a simple, inexpensive and generic method. But first, what is the CISS effect? Electron transfer is a process by which energy and information are transferred from one place to another in living organisms and electronic devices. The chiral-induced spin selectivity, or CISS effect, has two main actors, chiral molecules and electron spin. Electrons have two important properties. They carry negative charge and they have spin. The spin is the angular momentum of the electron. Like a spinning top that can rotate clockwise or counterclockwise, referred to as spin up and spin down. It behaves like a small magnet. Quantum mechanics shows that two electrons can occupy the same volume if they have opposite spins. When two electrons have the same spin, they repel each other. How do the chirality of molecules and spin relate? Chiral molecules have two different symmetries, similar to right or left-handedness, which are called enantiomers. When electrons are moving through chiral systems, they behave as if there is a magnetic field acting on them. This magnetic field interacts with the magnetic dipole of the electron, namely with the spin of the electron. Therefore, when an electron is transferred through chiral molecules, one spin is preferred over the other. Which spin is preferred depends on the handedness of the molecules, right or left hand-like symmetry, and on the direction of motion. So, chiral molecules are like spin filters. This is the CISS effect. The CISS effect helps to eliminate contamination of undesired substances. But how? Let's assume that we start with a neutral molecule which doesn't have net charge. When molecules interact with other molecules or a surface, the charge in the molecule is polarized so that it has a positively charged pole and a negatively charged pole. This is done by moving electrons from one side of the molecule to the other. Because of the CISS effect, if the molecule is chiral, the electron motion is accompanied by spin polarization. The spin associated with each charge depends on the handedness of the molecule. Now let's discuss the interaction of chiral molecules with a magnetic surface. In magnetic surfaces, all the spins are aligned in the same direction. As the molecule approaches the surface, it becomes electrically polarized, and depending on its handedness, the spin of the pole pointing towards the surface can be the same or opposite to the spin of the electrons in the surface. If the spins are opposite, they can occupy the same volume, and therefore the molecule and the surface attract each other. If they are the same, they would repel each other. Hence, if a solution contains both enantiomers of a given chiral molecule, it is possible to separate the enantiomers by magnetic surface that attracts one and repels the other. Since life is based on molecules with only one enantiomer, namely chiral molecules that have specific handedness, it is important to manufacture drugs of the same handedness. Typically, in a chemical reaction, both enantiomers are equally produced in a mixture. The undesired enantiomers may cause side effects disastrous to living beings. The CISS effect helps the chemical and pharmaceutical industry achieve an inexpensive and generic method for enantiomer separation, enabling a future of safe drugs, pesticides and fertilizers with no negative side effects to people, animals and our environment. If you're interested in the CISS effect or the enantiomer separation technology, contact the inventors, Ron Naman and Yossi Paltil.